Hey there, Mr. Miller here, and today we're going to be talking about continuous exponential growth and decay. We said a neighbor's house had been increasing in value by 5% each year. What does that mean? Let's pretend their house starts at $172,000 in value. We'll find out how much it should be worth in 6 years if the growth trend continues. Now, we've previously talked about discrete change, but in this case we're talking about continuous change. You don't wake up tomorrow and your house is worth way more. It happens little by little. You plant a tree, you repaint a room, new jobs open up in the area, or other homes sell. Continuous growth is a smooth increase, which is what we'll be talking about. This is our formula. Now we need calculus to prove this is our formula, and we're not ready for that. So today you're just going to have to take my word for it. Khan Academy does a pretty sweet video for the calculus if you're interested later. For our exponential growth formula, P is the final population, value, or cost, depending on what you're talking about. P sub 0 is the starting amount. R is the rate of change. This can also be listed as K for constant of growth. It is the same thing either way. And T is the time. T is almost always the time. So remember, our house is worth $172,000. We're going to substitute that in for the starting amount, or P sub 0. Then our value is going up by 5%, or 0.05 in decimal form. And we'll put that in for our R. Lastly, we're going to want to know what the value is in 6 years, so we're going to plug in 6 for time. And that's it. We can just type this into our calculator and find out what the house will be worth. And it's more than $232,000. That's about $60,000 worth of growth. And that's amazing for your neighbor. But let's talk about a more sinister situation. The Joker laces Gotham's water supply with a compound that makes people laugh uncontrollably. Over time, fewer and fewer citizens are affected. 735,000 citizens were initially dosed with the compound, and by the end of the second day, 500,000 people were still laughing. Presuming the change is represented by an exponential curve, how many days will it be until only 50,000 citizens have the giggles? Now, we know how many people were dosed right at the start. 735,000 people in Gotham. And we know how many people were still affected by day 2. 500,000 people. We also know that at some point, 50,000 people are still affected. So let's make a table of our data. We're going to use this table and our exponential growth formula to solve our problem. Now we can't solve for when 50,000 people are affected because we want to solve at the time, but we also don't know what the growth rate R is. So we're going to have to find R first. We can do that by solving our equation looking at the second day. We know that on the second day, 500,000 people were still laughing. We can substitute that in for our current population. We also know that we originally had 735,000 people affected, so we can substitute 735,000 in for our starting population. And last, we know it's the second day, so we can substitute 2 in for T. We've got to deal with that pesky Euler's number, so let's divide both sides by 735,000. That gives us 100 over 147 equals e raised to the r2 power. If we take the natural log of both sides, we now have the natural log of 100 over 147 equals 2r. Divide both sides by 2, and yeah, that's still a big old mess. But you can plug the natural log of 100 over 142, quantity divided by 2, into your calculator. And you're going to get about negative 0.1926312. Our growth constant being negative makes sense, and this is important. Our growth constant being negative makes sense because our population isn't growing, it's shrinking, it is contracting. So after we found R, we have everything we need to find out when 50,000 people are infected. So let's take a deep breath. And let's clear our board. Again, we're going to start with our formula of P equals P sub 0 times e raised to the r2 power. Our starting population, P sub 0, is still 735,000 people. That's not going to change. We can plug that right in. We have found our constant of growth. That's what we just did. That is that negative 0.1926312. That is our R, our rate of change. And we want to know what the time is when the population is 50,000 people. So we can substitute that in. We don't have time, but we can solve to find out. Again, we're going to divide both sides by 735,000. Reducing our fraction, putting it in simpler terms, gives us 10 over 147 equals e to the negative 0.1926312 t power. we're going to take the natural log of both sides, and we're going to divide both sides by that constant of growth. Again, we have a really big mess, but we can plug in the natural log of 10 over 142, quantity divided by negative 0.1926312 into our calculator to get almost 14 days. After 2 weeks, 50,000 people are still laughing. It is an awful 90s sitcom up in Gotham. So that's it for today. Remember, if the change happens in big spurts, we use the discrete exponential change formula. But if the change happens little by little over time, use P equals P sub 0 times e to the RT power. Happy mathing!